Any questions from the previous class? Okay, so in the last class we discussed affine sets. We said that a set is affine if given any 2 points, the entire straight line passing through those points also lies inside the set. And we defined the affine and convex hull, and we saw that affine sets are essentially shifts of vector subspaces, right? So that essentially characterizes all possible affine sets. We saw a number of examples, and towards the end we discussed what limit points were. So given a particular set, all possible points that could possibly be limits of sequences originating from that particular set is called a limit point of that set. So of course every point within the set is a limit point of the set, but potentially you could also have points outside the set which are also limit points. But then the set of all limit points is equal to the set itself if the set is closed. Okay, and the closure is defined as the set of all possible limit points of a given set. And it turns out that the closure is just the smallest closed set containing S. Okay. So just as we define the closure, we can also define the interior of a given set, and that is simply the largest open set which is contained within the set S. So given an arbitrary subset S, we say that the interior of S is the largest open set that is contained in S. Right. So given a point, we say that it's an interior point of the set if, intuitively speaking, it doesn't lie on the boundary, right? Which means that given this particular point, I can draw a ball of whatever, it could be like a really small radius, but there is a ball around it which is contained strictly within the set S. So X in S is an interior point if there is some epsilon greater than 0 such that the open ball centered at X and having radius epsilon is contained within S. So this is just the set of all vectors y such that the norm of x minus y is less than or equal to epsilon. And in general, this could be any norm. It doesn't necessarily have to be the 2 norm. If x is an interior point according to one particular norm, let's say the L1 norm, then it's also an interior point with respect to the L2 norm. Okay. And in general, now you have the closure of S, and I've defined what is called the interior of S. So how would you define the boundary of a given set? Yeah, so intuitively it should be the closure minus the interior. Okay. Let's take some examples. Let's start with the open interval from 0 to 1, or maybe the half closed interval from 0 to 1. What is the closure of this? So this is my S. Is this set closed? Yes. Why is it not closed? So there exists one limit point at 0. So I can construct a sequence originating from S, but that converges to a point that is not in S, which is the element 0. And what is the smallest closed set containing S? That would be the closed interval from 0 to 1. Similarly, what would be the interior of S? So the interior is the largest open set which is contained within S, right? So that would be, what is the largest open interval inside, or largest open set inside S? That is just the open interval from 0 to 1. Okay, and what would be the boundary of S? The elements 0 and 1. I mean, you can also view this pictorially. So I have 0, I have 1. The set is the open interval from, so everything that does not contain 0 but all the way up to 1, right? And evidently in this set the boundary should be the extreme points, right? 0 and 1. Given any interval, or given, so yeah, given any arbitrary interval, the interior would just be the open interval except the endpoints. The boundary would correspond to the endpoints, and everything including the boundary would just be the closure. And that's true for any interval, correct? Let's take something in R2. Let us consider the square in R2. Again, just visually you can see what the closure, the interior, and the boundary should be. So what would be the boundary of this particular set? The boundary would just be the set of these white lines that I've drawn over here. Everything that is enclosed strictly within this would be the interior, and put together that would form the closure. Okay. So things can get a little more tricky. So suppose I take S is equal to the set of all rational numbers. Right. So what is the closure of S? This would be R, the set S plus the set of all include all the set of all limit points. That would be the set of real numbers. But what is the interior? Where it be Q? Yeah, 5. Why? Correct. So to take any point in Q and draw a ball, no matter how small, around it. this will always contain an irrational number, right? So which means that you can't find a ball that is contained within the set of rational numbers. So the interior is in fact empty. So this is a weird case where every set is a boundary, every element is a boundary point. The set of all boundary points is R. Okay. But these, I mean, you can think of this as a sort of a pathological example, because we will generally consider points that are, or consider sets that are continuous. Okay. This in some sense is discrete, right? Okay, but all of this is fine. Okay, so let's take another example. So let me take R2. But in R2, I want to consider some line segment. What would be the closure? The line segment itself, assuming that it also includes the endpoints. So this would just be equal to S. What would be the interior? Yeah, empty. That would just be the empty set. And the boundary would therefore be S. Correct. But now this makes it a little difficult for us, because in general, when so the sets that we're considering, right, all of these would correspond to a set of constraints in our optimization problem, and we want to distinguish between points. So for example, this could correspond to some set of inequalities, right? For instance, you could have inequalities of the form, let's say one would be an equality, let's say 2x plus 3y equal to 1, x less than or equal to 2, and maybe x is y is less than or equal to 5. Maybe these are the set of constraints that I have. Now, what would I classify as a boundary point? Intuitively, I'm not making a rigorous statement over here, but what points would you classify as boundary points? Right. So if all of the inequalities are satisfied with equality, you would consider that to be some sort of an extreme point. But what you want as an interior point is at least one of these inequalities are being satisfied strictly. Right. One of these inequalities is a strict inequality, and we want to distinguish between these two. But that will not happen if we use the standard definition of closure and interior. For this, we need something slightly different. So for this, I'll define what is called the relative interior of a set. So the definition is very similar. So the relative interior of S and I denote this by RELINT of S. This is the set of all X, which again these are points around which you can draw a ball of at least some positive radius, but the ball is now not in Rn or Rd, not in the ambient space, but rather in the affine hull of S. Okay, so such that a ball of center at x and this intersected with the affine hull of S is contained strictly within S. To understand this, let's go back to our earlier example of a line segment in R2. Okay, so this is the set. What would be the affine hull of this particular set? Yeah. Yeah, so the entire line that passes through this line segment, or the line that contains this line segment. So this white line segment is my S, and this entire green line, this would be the affine hull of S. So if I take any point in S, what would be the intersection of the ball with the affine hull? What would that correspond to? Yeah? Correct. What points? I want to characterize what kind of points. Of course, there'll all be points on this line, but can you say something more specific? Okay, convex. Something even a little more specific? No. So I want to understand objects of this particular form for this example. So in R2, what is a ball? No, what does it look like? I'm talking about geometrically, right? These would be circles, right? Circles without the boundary, open balls, correct? What would be the intersection of that ball with this particular line? Yeah. So I take a circle, right? I mean, the entire circular region. When I'm saying the circle, it's not just the boundary. I remove the boundary and everything in between, right? I take the intersection of this particular set with, suppose the center of the circle is somewhere on this particular line, right? So I take a point on this line. I look at this entire region. What is the intersection of that with this straight line? That would be just a line segment, right? There would also be another line segment without the end point, correct? So that would be some particular line segment, correct? So any line segment can be written as in this particular form, correct? So now what would be the relative interior of this particular set S if S is a line segment? Okay, it's already a convex set. The line segment is already convex, right? Again, geometrically. Would it be S itself or something else? Sorry? So it is a set of all points in this set within which I can draw a ball, right? And which is still contained in S. Yeah? Correct. So it would be the segment without the endpoints, right? So in fact, suppose that this came from a set of inequalities, let's say x plus 2y equal less than x plus 2y equals 1, say x is less than or equal to something, say 3, and maybe this is some 5. X is less than or equal to 3, y is less than or equal to 5. Suppose these three inequalities correspond to this particular line segment. Okay, what would the relative interior correspond to? It would be this line segment without the extreme points, right? So what would happen? If you had to algebraically describe the relative interior, what would it be? So geometrically, we know that it's this line segment with the endpoints removed, right? So what would be the boundary points? Just take this. I want you to just explain in terms of this example. Yeah, so that would be 3 minus 1. Okay, so I think fine. So that would be 3 comma, so x equal to 3, y equal and y satisfying this, so that would be 3 comma minus 1, and this would be the boundary, right? The boundary of S would be this, and what would be the other point? 5 comma minus 2, right? So, well, I think it would be the other way, minus 2 comma 5. So x plus 2y equals 1. So when x equal to 3, this would be one of the extreme points, x equal to 3. What would y be equal to? That would be equal to minus 1. But when y equal to 5, what would x be equal to? So y equal to 5, 10 minus 9. Right? Fine. So this would be the boundary, and what would be the interior or the relative interior? Yeah, correct. Which would be, I mean, in terms of, you have to algebraically describe the set. So it is the set of all x comma y satisfying x plus 2y equal to 1, right? So with just this, that would give me the affine hull. X would be strictly less than 3 because it doesn't include the boundary point, and y would be strictly less than 5. Ah, you're right. I think I should have. I think the slope is. Y should be. No, y should still be less than 5, no? Correct. That would be equivalent, right? Because this constraint takes care of that. So all I need to have is x less than 3 and y strictly less than 5. Right? Any questions? Okay, so let's again let's see some more perhaps geometric examples. Let's take the following. Let's consider this weird looking set over here, which is dark. Let's try to plot that separately. So this set is just, I take a piece of paper, I cut out this shape, right, and this would be the set. Is this convex? Yeah. Yes. No. This is not a convex set. Okay. What would be the interior of this particular set? The interior. Would that be the interior or the relative interior? That's why I want to distinguish between the interior and the relative interior. We're talking about sets in 3D, right? So the interior would be the solid region inside it. This is not a solid region, so it's empty, right? The interior is empty. But what would be the relative interior? Yeah, so this black region except the boundary, right? Except this particular boundary. Okay, so this is sort of a flat piece of paper. What would be the affine hull of this particular set? Right, so that would be the plane that contains this. Right, which is this, which would be this particular plane over here. Correct, so that's to get intuition. Let's look at one other example. I take another sort of piece of paper. Is this set convex? Yeah, it's not convex. This is again, it's a two-dimensional set over here, but you can look at it this way. So think of it as though it's like a lace chip, right? That's one way to think about it. Okay, so what would be the interior of this particular set? Empty, right? What would be the relative interior of this set? That's where we need to be a little careful. What is the affine hull of this particular set? Yeah, so this is not, so in most common definitions, this would be a two-dimensional object, right? Because it's obtained by, I take a piece of paper, I cut it, but I also folded it a bit, right? That's why it is not flat, right? It's bent. So in this case, the affine hull would be the entire of R3, right? And in R3, this has, the interior is empty, right? So in this case, the relative interior is in fact empty, and all of these points are boundary points. That is why if you're not considering convex constraints, right, if the corresponding set is not convex, then this notion of interior and relative interior may not be very useful. The definitions that we've made in the sense of saying that something is the dimension of the set. So we talked about the affine dimension, right? This set has affine dimension equal to 3, right? Because the affine hull is the whole of R3. But I mean, geometrically, we see that it's actually a two-dimensional object. So the affine dimension could potentially be different from our intuitive notion of dimension. but these two correspond if the set is always convex. Okay, so these are definitions that are helpful when sets are convex, but otherwise things may be a little different from our intuition. Okay, so this is an example where the relative this set is in fact two-dimensional, but the affine dimension is equal to 3. Therefore, this set has an empty relative interior, and every point is a boundary point. Okay. So let's again try to look at things from a slightly more algebraic perspective. So consider this set of all points in R2 for which the 2 norm of x is less than or equal to 1. In fact, you can think of this in Rn. What would be, so what is the closure of S? Yeah, correct. So it's S itself. Correct. This is, as you said, it's a circular region. So the circular region, including the boundary, corresponds to the closure. What would be the interior? This would be the set of all x such that the 2 norm of x is strictly less than 1. Okay. Again, that intuitively just corresponds to, geometrically it corresponds to the circular region except the boundary. And so in this case, what is the relative interior of S? Yeah. So if the interior is non-empty, then the relative interior is always going to be equal to the interior of S. And what is the boundary of S? So it is a set of all x for which the 2 norm of x is exactly equal to 1. Okay? It's going to be all of Rn. In this case, R2. Okay? What about this particular set? So the set contains just 3 points, 1, 2, 2, 1, and 3, 1. What is the closure of S? Yeah. I mean, it's just 3 points, right? There's only one set. It would be S itself. Right? Yes. So every finite set is closed in Rn. Okay. What would be the interior of S? It would be empty, right? What would be the relative interior of S? That would also be empty, and so every point is a boundary. Okay, let's look at another example. Set of all x such that x1 plus x2 equal to 1. Okay, what would the affine hull be? What points are these? Yeah? Yep. So do these 3 points lie on a straight line? They don't, right? So the affine hull would be equal to R2. But in case these 3 points were all on a straight line, let's say it is 1 comma 2, 2 comma 1, and 1 comma 2, 2 comma 1, say 1.5 comma 1.5, right? Then the affine hull would just be the straight line passing through those points.
So, if we take any 2 points from the test,
Correct.
then it will be more R squared.
If you take any 2
Any
points,
2 points, 3 points are there in this. So if
correct.
you take any 2 points from this,
Yes.
the affine hull of those 2 points will be 4 R.
No, right? Why?
In this sense,
Um,
take 1 comma 2 and 2 comma 1.
I'm not sure what you mean by if you take 1 comma 2 and 2 comma 1.
If you construct it,
Okay, so let's say S equal to,
1 comma 2.
correct. So S equal to just 1 comma 2 and
2 comma
2 comma 1.
affine
What would be the smallest affine set containing these 2 points? It would just be the straight line passing through these 2 points. So it would not be all of R2. Right? So the affine dimension of S is just 1. This holds true in Rn. Generally, if you take 2 points, then the affine dimension is always going to be equal to 1. Okay, what about this example? X closure of S is S itself. The interior is empty because it's not in R2 it's not solid. The dimension is effective. It's a one-dimensional object in R2. But what is the relative interior of S? S itself. Right? So you can think of it as a bijective mapping between this and R. Right? So R is both open and closed. So the closure of S is S itself. The relative interior of S is also S itself. And this has no boundary points. Yes. Closure. So sorry, you're right. So I would say the relative boundary is it.
affine hull of this set S is
The affine hull would be S itself. Okay, again, this is just a line segment. The same thing, you can work this out yourself. Okay. Any questions? All right, so you can work these 2 examples out yourself. It's pretty straightforward. But now let's move to a different class of sets. Right? We defined convex sets, we defined affine sets. We define now what are cones. Right? Again, we think of it geometrically. So S is a cone if the following happens for all x in S and alpha greater than 0, greater than or equal to 0, alpha x is also in S. So geometrically, let's take R2 or Rn. What does this mean? Suppose I take a point x, right? Well, it could be, let me talk a point over here, right? This is my x. What is the set of all alpha times x, for alpha being between 0 and alpha greater than or equal to 0? Correct. So it's effectively a ray, right, shooting from the origin and passing through x. Right, so this is the set of all alpha x, alpha greater than or equal to 0. So S is a cone only if the ray from the origin passing through the point lies completely inside the set for all points, right? So the cone is convex if it's also a cone, right? So a set which is both convex and a cone is called a convex cone. An important property is, so we'll define a conic combination. So all linear combinations of the form I equal to 1 to n general m theta I xi, where each of the theta i's is greater than or equal to 0 for all I. This is called a conic combination of x1 to xm. Okay, so it's a affine combination if all the coefficients sum to 1, but they can be arbitrary real numbers otherwise. In addition, if all the coefficients have to be non-negative and sum to 1, then that's called a convex combination. It's a conic combination if all the coefficients are greater than or equal to 0. Okay. So if S is closed under conic combinations, it is a convex cone. No. Do you see why this is true? So suppose that S is a convex cone. We want to show that it's closed under all possible conic combinations, right? So effectively, if x1 through xm are in S, and theta 1 through theta m are all greater than or equal to 0, then we want to show that summation over I theta I xi is also in S. Can you see why that is true? You know that S is a convex set, right? So S should be closed under convex combinations. So from theta 1 to theta m, can you construct a convex combination? Yeah.
X is a closed under convex combination, then it is a convex string.
So if S
It's closed under
conic
conic
combination, correct?
It's a convex.
Yes.
But we are using the fact that X is a convex.
Which one?
Suppose
Okay. So let me make the following. So S is closed under conic combinations if and only if it is a convex cone. I want to prove both ways. Okay. So let me prove one way first. So suppose that S is a convex cone. So it's closed and a convex set. How do I show that it is closed under conic combinations?
Exists some conic combination. That's the
Okay.
it's to get this. So we consider for conic combination, we take theta vector
Correct.
between 0 and 1.
Correct.
They're all positive.
Yes.
So that exists, then we can substitute a particular set of coefficients.
But you're saying that it holds only for restricted thetas? So simple, just apply these two properties sequentially. First convex, then cone. So consider, I want to show that summation I equal to 1 to m theta I xi. I want to show that this lies in S. Correct? How do I generate, how do I get a convex combination from this, from a conic combination? I could potentially just normalize this. Right? So suppose I write this as theta 1 plus theta 2 up to theta m. I multiply and divide by the sum of all the theta i's. Summation I equal to 1 to m theta I divided by theta 1 plus theta 2 up to theta m times xi. Okay. What can you say about this? What kind of a combination of xi is this? It's a convex combination of x1 through xm, right? So this is a convex combination, and therefore this convex combination lies inside S, right? But then what am I then doing? I'm just multiplying it with a positive real number, right? So the product should also, since it's a cone, the product should also lie in S. So this vector always lies in S for every theta 1, theta 2 up to theta m. Is that okay? I'm first using the property that it is a convex set, because if it is a convex set, then if x1 through xm are in S, then this vector also lies in S. If it is also a cone, then multiplying it by scaling it up by any positive number also make sure that it lies in S. Right? So this will always lie in S. What about the other way around? Now suppose it is closed under conic combinations. Right? It should be a cone because it means that if x lies in S, then theta x also lies in X for all theta. Right? So this is a cone. It's closed under all possible conic combinations, but the set of convex combinations is just a subset of the set of all conic combinations. Right? So it should also be convex because we're only imposing additional restrictions, right, of the kind of linear combinations we're allowing. Well, take any convex combination. Every convex combination is also a conic combination, right?
The convex is
Correct. True. But I'm saying that all conic combinations also lie inside S, right? So take any x1, x2 or x1 through xm. I know that all conic combinations of x1 through xm lie in S. But what if I take a convex combination of x1 through xm? That should also lie in S because every convex combination is also a conic combination. Right? Does that make sense? Right? So this is in fact the easier side of it. In which convex? No, no, right?
summation of
And the entry should be greater than zero, right? Those are affine combinations. Let's see some examples of cones. What about is a straight line a cone in general? Correct. So if it passes through the origin, then that would be a cone, right? So what is the equation of any straight line passing through the origin in Rn? Equal to yeah. So in R2, the y is just equal to y equal to mx, right? Which means that if x comma y lies in uh, in the line, then alpha times x comma y should also satisfy this equation, right? But in general, what is the equation of a straight line? Okay, I'm talking about in Rn. Yeah, double transpose X. Um, okay, so what would W be? Or in other words, what would be the dimensions of W? Think about it. So, okay, what is the equation of a straight line passing through, or in general, a straight line in Rn? Okay, so it is a set of all x such that W transpose X equal to B. Again, what are the dimensions of W and B? N cross, which is N cross N? Um, sorry, W is N cross 1, X is N cross 1, and B is a scalar. Are you sure? Would this correspond to a straight line? Okay, what kind of a set does this describe? Set of all W transpose X equal to B. Yeah, what you've given me is a description of a hyperplane. So both the straight line and the hyperplane, what kind of sets are these? Among the classes of sets that we've seen. Okay, the convex, yes. They are affine, right? They're both affine sets, but they have different dimensions. So in general, how do you describe a general affine set? I know, but in terms of, say, linear equations. Correct? So what would A and B have to be? Yep. So in general, if I had to think of a affine set of having affine dimension some k, how would you describe that? Yep. So some W times X equal to B. So X would, well, X is always in Rn, right? All that you can determine is so the whatever affine set is determined by W and B, right? So that would be a full rank K cross N matrix and a K cross 1 matrix, right? And you also have to ensure that these are consistent. Now, for a straight line, what would the equation be? Yeah. So what would you say about W if this had to describe a straight line? It would be a rank one matrix. Again, would that give you a straight line or would that give you a hyperplane? So what is the dimension of, what is the affine dimension of a hyperplane? N minus 1. What is the affine dimension of a straight line? 1, right? So a one-dimensional object would be the null space of an n minus 1 rank matrix, right? So in general, so W would have to be an n minus 1 by n full rank matrix. And B corresponds to a shift. Wx would equal, that's what I was going to come to. Wx equal to 0 would correspond to a straight line, but what straight line? That would be a straight line passing through origin, right? So going back to my original question, the equation of a straight line passing through the origin this would just be the set of all x such that W times x equal to the 0 vector, where W is an n minus 1 rank matrix. Right? If you're still not convinced, then take an example later on. Take, let's say, in R3, right? Because that's the interesting case. So in R3, take a rank 2 matrix and try to plot the set of all points satisfying W times x equal to 0. Okay, for example, you could just take 1, 1, 1, 0, 0, 1, say. Right. Try to plot the set of all x satisfying this matrix times x equal to the 0 vector. Also, this matrix times x equal to, let's say, 1, 1. All right. Okay. So coming back, is this a cone? Yeah. So this will be a cone. In fact, take any vector subspace. Is this going to be a cone? Maybe. How many say that a subspace is always a cone? Take any vector subspace. This vector subspace will be a cone. How many say yes? How many say no? What about the rest? Okay, why is it a cone? Yeah. Okay. But something more simple.
Scalar
Correct?
from the real field should belong in that subset.
Yes. Yeah. So in general, all the kinds of sets that we're considering, they're closed under restricted kinds of linear combinations, right? But vector subspaces are closed under all possible linear combinations. So vector subspaces are affine, they are convex, and they are cones. Right? But what about a straight line that does not pass through the origin? Is that a cone? No, right? Because a cone should always contain the origin. Now, can you give me some other example, non-trivial example of a cone? Consider R2. Yeah? Okay, so again a subspace. Let's consider R2. Can you give me an example of a cone which is not a straight line? A half space. Okay, yes. Any half space? For example, if let's say I consider this half space. Is this a cone? Yeah. Okay, so let me consider this. Is this a cone? Would this be a cone? It wouldn't be, right? Because, for example, let me take this particular point over here. The entire ray passing through this should be contained in the cone, which is not the case. So, any other example? I mean, what would be, suppose I asked you to draw a cone in R2, how would you draw it? Okay, first quadrant, but in general, how would you draw a cone? A ray and rotate it through an axis? So it would look something like this, right? So is this, I mean, I drew something over here, but is this a cone according to our definition? It is, right? Because it contains all rays. Is it a convex cone? Yeah, it is, right? Is it a polyhedral? Yeah, how many say yes? Okay, how would you describe this as a polyhedral? I know, but which, so, okay, let's take this particular case. It's bounded by how many half spaces? So it's an intersection of half spaces. Okay, and how would you describe that? So suppose that this line is, say, A, whatever, A transpose X equal to, fine, what would this be? What should be the right hand side? 0, and this is some B transpose X equal to 0. Okay, how would you describe less than 0, right? So A transpose X greater than 0 would correspond to the entire region above this, and B transpose X less than 0 would correspond, or less than or equal to 0 would correspond to the entire region below this. So this is a polyhedral cone, right? It's also a convex cone. Can you give me an example of a non-convex cone? I mean, this example is clear to everyone. So this is an example of a cone. This is a cone. It is convex. It is also polyhedral. So this is called a polyhedral cone. So in R2, can you think of a like geometric or visual non-convex cone?
Convex.
Okay.
That's we use the region such that the use becomes diameter between the two length more than 180.
Okay.
This
Correct. So this would be an example of a non-convex cone. Right, so this entire region. This is a cone, but it's not convex because if I take any 2 points over here and I draw the straight line joining them, then that's not contained inside the. So this is a non-convex cone. Any other ways of generating non-convex cones? What is the simplest cone in R2? Yeah. Okay, straight line. One that is not fine. Just a ray, right? Any ray passing through, starting from shooting out of the origin, that is a cone. Correct? So any ray shooting out of the origin is a cone. What if I take the union of two different rays? Is that a cone? It is a cone. Is it convex? No. Right? So in general, you take any two cones, the union of those two cones will also be a cone. But it need not be a convex cone. We'll see some more examples of cones. But exactly as we defined fine and convex hulls of sets, we can also define the conic hull of a given set as the smallest cone that contains the given set S. Or I should say the smallest convex cone containing S, and this is also equal to the set of all possible conic combinations of S. And in fact, you can think of this geometrically, right? So let us take some weird looking set in R2. Let me suppose that I have this particular set. What would be the convex hull of, so what would be the affine hull of this particular set? it would be R2, right? What would be the convex hull of this particular set? I mean, it's difficult to describe it, but that would be if you just sort of smoothed this out, right? This is what the convex hull would kind of look like. What would the conic hull look like? Yeah, so correct. So you take a ray that looks something like this, and another ray that takes the other extreme point. So the entire region between these two rays would be the conic hull. Exactly. So the convex hull will be a subset of the conic hull. So you can think of it as the smallest cone containing the convex hull of S. Let's look at another example. Suppose I take just a subset of points. Right, I take let's say I just take these 4 points. What would be the convex hull of these 4 points? Just the polygon that the extreme points correspond to. This would be and the conic hull would effectively be this particular cone. What would be the smallest cone containing these 4 points? Correct. So the smallest cone containing these 4 points would be just 4 rays, one passing through each of these points. Right? So the smallest cone containing the set could potentially be different from the smallest convex cone containing these points. Right? And this is in fact the conic hull.
Is there a definition for small cone containing
Not that we're going to use it. No.
can that be convex conic by minus
No, right? Well, that would not be a cone at all, right? Because this is the conic hull. This minus the convex hull would just be the cone with this patch removed. Right? That would not be a cone. Any other questions? Okay, so right. So as we've seen, any vector subspace is a convex set. It's an affine set. It is also a cone. Let's consider the norm cone, which is the set of all x comma t. So x is in Rn, or x is in, let's say, Rn minus 1 and t in are greater than or equal to 0 such that norm x is less than or equal to t. So this is a vector in Rn, right? I take the first n minus 1 components, I call it x. The last component I call it t, and so this is x set of all x such that norm x is less than or equal to t. In R2, what does this look like? So it is the set of all in R2 this is the set of all x comma y such that norm of x, which is the absolute value of x, is less than or equal to y. In R2, doesn't really matter. I mean, because this norm is over R1, so that doesn't really matter. Every norm will correspond to a particular norm code. So what does this look like? Yeah, x is between y and minus y. So visually, like geometrically, what does it look like? Okay, so I have lines. Can you describe it? Okay, I have y equal to x and y equal to minus x. Right? What region is this? Again, all of this makes sense only for t greater than or equal to 0. So y should be greater than or equal to 0. So what region is this? It's in between, right? So it is in fact this region over here. In R3, what would this look like if I take the L2 norm? Yeah, so that would correspond to your ice cream cone. So obviously, by definition, it's a cone, but you can still verify that it satisfies the properties. So check. Is this set affine? Yeah. Will it ever contain the entire straight line? It won't, right? Because t has to be greater than or equal to 0. So this is not affine. Is it convex? It is convex. Again, prove this. Is it a vector space? Obviously. No, right? If it's not affine, then it can never be a vector space. Right? Okay, so I'll leave this as an exercise. The set of all possible symmetric matrices. In which? Okay, if suppose that x comma t lies inside the cone, will minus x comma t lie inside the cone? Or minus of x comma t. So t always has to be greater than or equal to 0. So the additive inverse, for example, is not present. And that's also the reason why it's not affine. Any other questions? Okay, so let's stop here.